Newtonian laws. Okay, so this is what the people thought up to 19th century, and then they thought that everything can be explained by this particular the Newtonian laws. Okay, but unfortunately, after discovery of the electrons and the the atom, which is composed of the electrons and the subsequent subatomic particles. So after discovering this, then there are quite mysterious questions need to be answered. Okay, there are many things we could not able to explain it. The first thing is the black body radiation that we could not able to explain it. The second thing is the photoelectric effect, the famous Einstein experiment, which has given set back to classical Newtonian mechanics. And the third is basic atomic theory itself. Okay, and the fourth one you have several things like Compton scattering, and then you have a light properties also like a diffraction, interference. All this also posed a great challenge to this Newtonian mechanics, and eventually the Newtonian mechanics could not able to explain all these experimental evidences. Okay, so that is the reason why you need to look for the alternative ones. So that alternative one theories has led to discovery of the quantum mechanics. Now, when it comes to now, what are the drawbacks you have? It, as I said, like black body radiation, right? So what is that black body radiation? Where exactly the Newtonian mechanics fail to explain this black body radiation? So when it comes to black body, whenever light interacts with any body, this is what we have discussed in the previous chapters as well, right? So there are only three things can happen. One is reflection, absorption, and generation. Okay, so now in principle all these three things it can happen simultaneously. Please remember, okay, in a certain body all these reflection, absorption, and generation all can happen simultaneously. But what you see, the light interaction with the any particle, any body, by only reflection. Okay, so there is no reflection, that you cannot really see. Okay, so therefore all that what you see is basically because of the reflection. Okay, now what is this black body? Okay, so if any object has no reflection, then if there is no generation, it would appear to be absolutely black. We call it as a black body. So which means basically, in other words, you can say that all incident light is totally absorbed. So that looks like a black body. But in general, the experimental evidence shows that the black body can generate light. In fact, it must, in order to maintain the equilibrium. So because it comes from the Kirchhoff principle, that is the amount of radiation being absorbed, whatever the amount of radiation you absorb it, you should actually at any frequency. Okay, that should emit it. Okay, so that's what the Kirchhoff law says. So a perfect absorber of light must also a perfect emitter. So therefore, the black body in general you can define like a perfect absorber and a perfect emitter of a light. That is what is black body, you can call it as. Okay. Now, because any black body is a perfect emitter, every black body should have the same emission spectrum, isn't it right? For example, when we say that a black body is a perfect emitter, so every black body should have the same emission spectrum. Okay, so which means basically when you give heat to the black body, then with the variation of the temperature, it emits the electromagnetic radiation. So but that electromagnetic spectrum, with respect to temperature, if you look at, then you can understand the things. Okay, so now how do you make the black body? That is one more tricky question you have to ask. So it's making a black body is a really a tricky thing. Okay, so now how do you make a black body? You just see this. So usual approach is to a metallic cavity. You take any body and make a small hole into that. Okay, the small hole into that, any light coming from the outside, going through this hole here, this hole. Okay, and this is a metal. Remember, this is a metallic cavity which I'm talking about. This is a metal body, you can call it as, and there is a small patch of hole you make it, and whenever light enters through this, it undergoes multiple reflections within this wall of the metallic, right? So therefore what happens is each absorption, each whenever it goes and hit the wall, then it get absorbed. So now you have a multiple reflections within this metallic body or cavity. So therefore, what happens is the all of the energy which is entered into that will be generally absorbed. So the chances of the incident light being reflected directly back through this hole is actually very less. So that's how you can actually design a black body. So any light being generated by the motion of electrons in the walls of the cavity will bounce around many times before it escapes through the hole. So that means even a small percentage of the light escapes or reflects back out of the this black body. Then before going to that, it actually undergoes multiple reflections. Okay, so in this way, a hole here, the hole acts like a black body, and the cavity is filled by the black body radiation. So by heating the cavity structure up to a uniform temperature, you can absorb black body radiating coming from the hole. Okay, now look at what is that you can actually see. If you a opaque object emits electromagnetic radiation according to its temperature. For example, you take any metal or any other opaque material, okay, or metal in a way. Okay, you take a metal and you just heat it. The moment when you heat it, this is what you see, the color becomes like a red. That means the light it is emitting is actually red in color. Okay, but if you look at the the temperature variation from there, you go on increase the temperature to that metal body, so it becomes like, once it becomes red, then after that it turns out to be elevation color. Okay, and still if you go on, even they give the temperature to that particular body, it becomes like a whitish in color. Basically it is white and yellow combination. Okay, so now if you look at the temperature with respect to temperature and wavelength correlation here, the the color red, red starts relatively cool compared to the yellow, and compared to blue and white, then sorry, yellowish and white, which is actually a kind of blue, so will be more high temperature it will emit. So that's what the correlation you can have it, and you can do this experiment at your home also. You can take any metal and you try to heat it. Okay, so it becomes, the color of that metal becomes like a reddish in color once you raise the temperature to a certain degree. Then it turns out to be yellowish in color if you further increase the temperature, and it can turn out to be white in color if you increase enormously the temperature. Okay, I hope you are getting what I'm trying to say. Is it clear how the variation of the color with respect to temperature is
Yes,
working?
sir.
Yeah. Now, the
So,
summary you can see with respect to black body. Okay, when an object is heated, it emits radiation consisting of electromagnetic waves with a broad range of frequencies. So frequency is nothing but like a energy which is emitted. Okay, measurements made on the radiation escaping from a small hole in closed heated oven or cavity, okay, shows that intensity of the radiation varies very shortly with the frequency of the radiation. The peak of the frequency distribution shifts to higher value as the temperature is increased. So that's what, when the temperature is increasing, the frequency is actually shifting to higher value, which means basically the color of the the body is actually changing. So frequency distribution of radiation only depends on the temperature. Please remember, that is what I'm talking. Okay, for higher temperature, oven glows in visible range. It appears red. Okay, and around 800 degrees, and regardless of what is inside, coal, glass or metal, the although it's a black body, it will be like a a reddish in color. Okay, now recorded color distribution radiation between near infrared into violet escaping through the opening in the 1890s. This is experiment people have conducted. Okay, so that you can see it here. So with respect to radiation, okay, this is the energy or the frequency with which it is changing. Okay, and with respect to frequency on the x-axis basically here. Okay, and that is at some particular temperatures. For example, at look at the intensity here at the 1000 Kelvin, and you increase the temperature to 1500 Kelvin, then the intensity is now even more. Now if you increase it further more, that is at 200 Kelvin, then it is the look at the intensity. Okay, so the total energy emitted increases, and the peak in the spectrum shifts to higher frequencies. Look at the peak here somewhere here. And if you increase the 1500, then the peak has shifted to this. And if you increase the temperature frequency to temperature here 2000, then peak has shifted to higher frequency side. That is what is happening here. Okay, so which means basically when you raise the temperature, the wavelength is actually going towards the lesser side, shorter wavelength side it is moving, or higher frequency side it is moving. Okay, now the explanation comes here. There is a paradox is involved here. Okay, now this behavior, what is this behavior? Energy per unit volume, which is calculated with respect to variation of the frequency at different temperature, explained by Rayleigh and Jeans. So he has derived a formula. Okay, so the equation agreed here, this behavior, whatever it is behavior here. Okay, so it's like from frequency variation from low frequency to higher frequency here. Okay, so the mathematical formula he derived, it agreed well with the observed frequencies spectrum at low frequencies. At low frequencies, the energy spectrum actually agreed well. Okay, so but okay, yeah, but shock at high frequencies. At classical physics predicted. So in general, what is that point I'm trying to talk about is, for example, at 1000 Kelvin, this is the peak you have it. 1500 you have it. 200 the peak has shifted even more. And if you still go on further increasing the temperature, the ideally what is supposed to happen, peak should shift it into the higher sides only, right? So the intensity is supposed to be infinity at very high temperatures. That's what the this particular behavior is talking about, correct? But so this lead to a catastrophe. What is that? So it's like at ultraviolet region, that means for a lower wavelength or a higher frequency, there should be a very high intensity should come. Okay, so what is that paradox is, if the religion's formula were right, it would be dangerous even to sit in front of the fireplace. But everyone agreed that the method was sound. They applied the method from statistical physics to the waves by analogy with Maxwell's gas particles, using the equilibrium of partition of energy. The total energy of radiation is distributed equally among the all possible frequencies. So what is that basically? Rayleigh said. So when you when you increase the temperature, the energy density should go to infinity. This is absolutely something shocking. Okay, so this is what theoretically he explained it. But when people did experiments on that, it actually did not follow. So this is the Rayleigh theoretical graph. And when you do the experimental one, what happens is after certain frequency, it has come down. So Rayleigh's formula did well in the lower frequency side. It is explained up to this lower frequency, but it has failed to the higher frequency side. That is the that is the thing. It has failed in the Rayleigh's mathematical formula. So this paradox, which is if you go on increasing the temperature, and if you go to the ultraviolet frequencies or ultraviolet wavelength, the energy density is supposed to reach to infinite. So this is what is called as ultraviolet catastrophe. Okay, so this experimentally proved to be wrong. Okay, so therefore now there is a correction has been done to the Rayleigh's mathematical formula, and that has been proposed by Max Planck. So the idea what Rayleigh has taken is, whatever the amount of heat you give it to black body, that is distributed equally among all the frequencies. Okay, so all the atoms will take equal amount of energy. That is the assumption Rayleigh has actually done. So now Max Planck has come up with something different idea. To get there, he tossed aside the assumption that energies are continuously distributed. It is not a same energy, it is going to be given to everybody. Instead, he assumed that the energy of electromagnetic modes in the cavity consisted of discrete packets. Discrete packets means each of this particle, all right, may not exactly take the same energy, but the energy will be absorbed in a discrete manner, and the energy of each packet is proportional to the frequency. That is what he said. So the energy is something like this: E is equals to 0, E is equals to h mu, and 2h mu, something like that he has proposed. Okay, with that modification, he has just altered that Rayleigh's mathematical formula and he has come up with something different. So this is the formula he has come up: the energy density. And this energy density formula only we have used for the, where did we use this one, this formula? Where did we use this formula?
In Einstein coefficient.
Einstein coefficients we have used it. Okay, correct. Okay, now with this formula it has exactly matched. Okay, experimental results matched with this particular formula. So this was the first use of the notation that is called quantization of energy. That means basically each of the particle, that is energy, will be absorbed with the frequency only, or multiple integral of frequency only. That is what is called as quantization of energy. So the first concept of quantization of energy is proposed by Max Planck. So that has given us that has given a satisfactory result to explain about the experimental evidence of that frequency versus energy distribution at different temperatures. So Rayleigh has chosen a classical mechanical perspective, that is all the energy is actually distributed equally. So that has actually come out to be wrong. And the moment when you introduce the quantization of energy, which is a quantum mechanical phenomena, so the moment when you introduce this one, then the experimental evidences has actually come out to be explained very well. Okay, now put it very in a summarized way, classical physics predicted that hot objects would instantaneously radiate away all their heat into electromagnetic wave. The calculations, which was based on Maxwell's equations and statistical mechanics, showed that the radiation rate went to infinity as the electromagnetic went to zero. Okay, wavelength, if you go to zero side, that means ultraviolet side, right? Ultraviolet region is where? Ultraviolet starts from something like 70 to 200 nanometers, right? So you go to lower wavelength size, the electromagnetic energy density is going to be infinity. That is what the classical mechanics talks about. This is what is known as ultraviolet catastrophe. Okay, now the energy spectrum is actually E is equals to 8 pi mu square kt by c cube. This kt is the energy distributed to each particle. Okay, so this is the classical theory, which is giving you the leading to the ultraviolet catastrophe. But experimental evidence was not not something like this, but it has actually, after a certain wavelength, it has come down. So this graph is with respect to wavelength. Please remember that. Okay, so Planck solved the problem by postulating the electromagnetic energy which is given to all the particles is emitted in the form of quanta, that is E is equals to h mu. So the Planck's formula, he has just modified this formula with this. So 8 pi mu cube by c cube into h by e power h mu by kt minus 1. So he has used Maxwell distribution functions, and then he used the quantization principle, then resolve the problem. Okay. So this is the Planck's experimental and theoretical curve. The complete curve is this one is experimental, and there is a dotted circles. That is what is your Planck's one. Okay. So this is what Planck's one. Okay, so data points coming from the Planck's hypothesis only. Okay, now just how do heated bodies radiate? This is very interesting actually. So from the experiments of Hertz and others, Maxwell prediction that oscillating charges emit, this we talked about basically, okay, in the polarization, I guess. Okay, so each atom is basically vibrating, and when the vibrating when wave is vibrating, you have electric field and magnetic field, both will be vibrating perpendicular to each other, right? And it is also perpendicular to the wave direction as well. And this when wave is vibrating, which means what? Basically the charges are vibrating, right? And because electric field and magnetic fields are coming from the moving charges only, right? So these moving charges oscillating or vibrating, this vibration is going to give you the electromagnetic radiation, has been confirmed here. Now, what is meant by the phrase black body radiation? The radiation from heated body depends on some extent on the body being heated. To see this, most easily, how different materials absorb radiation. Something like glass seem to be absorbed light hardly at all. Light goes right through the glass material. For example, if you shine, metallic surface, if you take any metal, light is going to be absorbed, either it gets reflected. Okay, for a black material like soot or light, heat are almost completely absorbed and the material gets warm. Okay, so that's what. So this is what all about your black body radiation. I hope you understand where exactly the paradox is coming, and where exactly the classical mechanics fail to explain the black body radiation in the lower frequency side, or the lower wavelength sides, right? It could not able to explain it. Okay, and how Maxwell or Max Planck has actually resolved this issue. I hope you understand this black body radiation. Is it clear? Is it clear?
Yes, sir.
Yeah.
Yes, sir.
Okay. This who is Abhinav Reddy? Is he from B section?
Yes, sir.
Is your problem solved?
Yes.
Huh? Is your problem solved?
Sir. Yes, sir. Yes, sir.
Okay.
I have reduced the size and I have uploaded, sir.
Okay. 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 So the next thing which classical mechanics could not able to explain is photoelectric effect. And now let us see what is photoelectric effect. So what is that? Basically, the 19th century understanding is whether light is a wave or particle. This is the debate, and I told you about this story also, the historical narrative also. Historically, while the young two-slit experiment is credited with confirming the wave-like nature of light, it is the photoelectric effect that shows that light also exhibits particle behavior. We call light particles as photons. When light was used to knock the electrons out of solids, the results were completely different than expected from Maxwell's equations. Okay, so that's what. Look at here. This is the metallic body. You have it. Okay. Now, if you incident the certain wavelength of the light onto this particular metallic body, there was no electrons were actually knocked out of the metals. But for a lower wavelength, or in other words, you can call it as high energy electromagnetic wave. If you incident on this electromagnetic wave, then electrons were actually able to emit. But if you increase furthermore the energy or decrease the wavelength, then the velocity with which the electrons are coming out was actually even more higher compared to the other one. Okay, so this is what the observation has come in the electromagnetic the photoelectric effect. So electrons will be emitted or not depends only on the frequency. So no detectable time delay in electron emission. That means as soon as you impinge your electromagnetic radiation on metals, then the electrons will immediately emit it. Okay. Now the frequency of the light required to get emitted the electrons is something is like mu is equals to mu naught. That is the threshold frequency which you're supposed to use. So that will be equal to E naught by H, because the Planck's constant, you already know that E is equals to H mu, and this threshold frequency should be equal to E by H. This is what is you're supposed to use it. Okay. Now this depends on the metal, because why it is metal? In each metal, as you know that there are many of the electrons are in the valency state, and then you have a binding energy with which the electrons will be attached to the nucleus. So therefore, at least you should give the minimum energy, that is the binding energy, in order to knock out the electrons from the outermost electrons, so outermost orbits. So therefore, that frequency is what is required to emit the electrons. Okay. Now, if you look at the photoelectric effect, the formula that is Ek is equals to h nu minus E naught. Here the or E naught, in other words, like kinetic energy of the emitted electron. The measurements were easy to explain if light is made of particles with the energies as Planck postulated. Okay, so therefore, with this photoelectric effect, it is confirmed light is both. It is wave as well as the particles as well. So the idea is very simple. What is that? Put it in very simple words. For example, what you have used here. So there is a metal. This metal is consist of particles that you know that, right? And there is a wave is interacting. Light wave is interacting. Okay. So now when light wave is incident on that metal body, what you supposed to expect if it is only a wave? So if wave is incident on something, you should expect wave supposed to come out, isn't it? When wave is incident on something, like light is passing through the glass, so light only comes out, right? But here, when light is incident on the some certain metallic elements, then light is supposed to come out, but that's not happening. Light incident on the metallic sheet, then the electrons are coming out. So the whatever input you have used is a wave, but output what you are getting is actually particles. So this itself is telling you that the light is not just only a wave nature, which is which is coming because of the photons here, and it also consists of particles, that is electrons here. Is it clear now? Why both are these?
Yes, sir.
Now, what are the questions you can actually pose here? For example, in the photoelectric effect, you take sodium metal and light shining, when you just incident light on this metallic sodium metal, then electrons is going to be emitted. So now the details of the photoelectric effects were in direct contradiction to the expectations of very well developed classical physics. What are the questions you have it? Okay, the electrons were emitted immediately. And there is no time lag. What is the reason? That's the question. Okay. And the second is increasing the intensity of the light, increasing the incident light. Okay. So increasing the intensity of the light, increase the number of photoelectrons, but not their maximum kinetic energy. Okay. No matter whatever the intensity you put up, but the kinetic energy of the emitted electrons was actually same. Okay, now red light will not cause the electron ejection, no matter whatever the intensity you use it. A weak violet light will eject only a few electrons, but their maximum kinetic energies are greater than those of intensity light of longer wavelengths. So these are the certain questions, the classical physics could not able to explain it. Okay, now photoelectric effect, that these questions actually are answered by the again Planck's hypothesis. Okay, and it is being explained very well by Einstein using the same Planck's hypothesis only. Okay, so light, it said that light is basically consists of photons and it is a kind of wave packets. That's what you can see it here. So it is like analysis of data from the photoelectric experiment showed that the energy of the ejected electrons was proportional to the frequency of the illuminating light. This showed that whatever was knocking the electrons out had the energy proportional to the light frequency. Okay. Now, for example, if one electron is actually knocked out of this metal, so that energy which is used is exactly proportional to the frequency of the light which is incident. Okay, so this remarkable fact that the electron ejection was independent of the total energy illumination showed that interaction must be like that, a particle which gave all of energy to the electron. So this fit well with the Planck's hypothesis, which is E is equals to h nu. The black body radiation experiment could exist only discrete bundles of energy. That means if you have only, the intensity is the only matter. So if you increase the intensity, the electron should come out. But that's not the case. As I said, like in the Planck's hypothesis, each atom will have the discrete energies. right? E is equals to h nu, E is equals to 2h nu, E is equals to 3h mu, like that. If you give that specific, for example, if there is in the sodium metal, if there is a electron which is having E is equals to 5h mu, that corresponding frequency only when you give, then the electron will come out. Otherwise, no way you can actually eject that electron. So this has again confirmed in the quantization of the energy in the metals, or in the quantization of energy exists everywhere. That is what proved, and the Planck's hypothesis gave that answer to these questions again. Okay, so this is again. Now, this is the same example I told you. Most commonly observed phenomena with light can be explained by waves, but the photoelectric effect suggests that particle nature for light. So, the electron ejected, which is actually the particle in nature. Okay. Now, this is another thing again. Photoelectric effect. The third one is problems with the atoms. Okay. So, what are that? So, according to Dalton and others, each material consists of very small basic constituents called atoms, which is electrically neutral. And Rutherford performed a scattering experiment by bombarding a gold foil by particles to understand the structure of such atom. Now, that experiment of the Rutherford concluded atom consists of very heavy and charged center, around which much lighter particles of opposite charges are moving. In other words, the nucleus is positively charged and the negative charged electrons are surrounded by this nucleus. Okay. Now, classical electromagnetic theory predicts that such a structure is going to be energetically unstable, because these electrons are actually negative particles and it is going to be attracted by the positive charges. So therefore, at some point of time, it should fall with it should be attracted with the positive charges, right? So this is what the problem with the classical physics, right? Moreover, classical electromagnetic theory predicts that when such lighter charged particles will emit or absorb electromagnetic energy due to their accelerated motion, they will form a continuous spectrum. This is another thing, okay? Because the idea, as I said again, the energy is actually same for every particle. That is the assumption you have it. If the energy is same for everything, the energy spectrum should be continuous and same for everything. So that's what continuous spectrum means. But it was shown that the spectrum for each different particle or electron at a certain energy levels is something completely different. This is another question, classical mechanics could not able to explain. Now this has been resolved by Bohr. Niels Bohr proposed a set of postulates with which he has able to explain the stability of the structure of atoms and the related experimental results for the atomic spectrum. These postulates say that these lighter particles, which we henceforth call electrons, are allowed only to travel in orbits around the heavily positive charges at the center that we shall henceforth call as nucleus, such that their angular momentum and hence energy is quantized and does not decay. It's not going to be decay. As a result, such electron does not decay energetically, and when they make transition from one orbit to another, they absorb and emit electromagnetic radiation also comes in radiation spectra or discrete quanta. Again, such postulates cannot be justified by starting from the classical motion of a charged particle, which means basically if you have a atom that is here, you have a nucleus that is positively charged, you have electrons over here, right? Likewise, you have it, and then you have the second one is composed of, what is the second one? Basically, 8 atoms you will have it, isn't it, right? Correct? The third one is, it goes with the formula that is 2n square. Am I correct? 2n square, right? Now, this electron can jump into the other state, or whether this one can come down only with the energy corresponding to E2 minus E1. That's all. So, which is equal to again h mu. This is again quantized. Okay. So, therefore, the electron can exist only at a certain energy levels, which is quantized ones. Okay. It's not going to be a continuous. That is what again the classical mechanics failed. Now, the quantization of angular momentum, Bohr's postulates. Okay. This I think I skip here this one because this is already you must be knowing the energy is quantized, that is minus 13.6 by n square into z square, and you have the same thing like the how your frequency is going to be quantized, and sorry, angular momentum is getting quantized, and how your the ridge constant and the frequency can be calculated. All these you must have studied in the intermediate basically. Okay, and you also know that when you have a hydrogen atom, there are Lyman series, Bauman series, Paschen series, Brackett series, and Nunn series. All these basically comes with this certain quantization only. So once one electron state to another electron state, if it is jumping, certain energy or frequency is released, right? So that's what related to one of the series. So I hope you already know that, and that corresponding energy will have consequences with the color of your light which is emitted basically. Okay, now we just put it in a simple summary. Classical physics predicted that the atomic electrons orbiting the nucleus would radiate their energy away and spiral into the nucleus. However, the energy radiated by atoms also came out in quantized atoms amounts, in contradiction to the prediction of classical physics. Right? And the Bohr solution was to propose that provided that the electron circulates in orbit was radii are satisfied, and Hooke rules known as quantization condition, that is L is equals to NH cross. Okay, so the orbits would be stable because of this quantization only. Therefore, atoms will have a discrete energy levels. So emit or absorb the light in the quanta by jumping between the energy levels. So that energy is corresponding to this minus 13.6 by n square only. So this is for hydrogen atom. Okay, and Bohr's theory was quite successful for the hydrogen atom, but was unable to explain the higher orbital number atoms. So, for example, helium atom, lithium atom, all these they could not able to explain these. Now the question is, why quantization? Quantization is a natural consequence of confining waves. Example, harmonics of a violin string. Look at how this is a fundamental one. The first harmonic is two notes, you have it. The second harmonic having three notes, right? So basically, the confinement is basically only certain standing waves are allowed. Like there is only one wave, there won't be a 1.5. No, so there won't be here two waves in between, and you have three waves, there won't be any like 2.1, 2.3, right? Such a numbers are not allowed here in the harmonic strings also. So only certain frequencies are allowed, therefore only certain energies also, because frequency related with energy, so therefore energy is also allowed only in a certain number. A solid is a huge box, so the allowed frequencies are very close together, and a continuous absorption emission spectrum is observed. An atom is a tiny box, so allowed frequencies are well separated, and the absorption emission spectrum consists of discrete lines. Okay, and the failures of this Bohr model. Well, Bohr was able to, explain the quantum theory of the atom, but there is a correction. You have it. Okay, so it fails to provide any understanding of why certain special lines are brighter than the other. There is no mechanism for the calculation of transition probabilities. When like electron jumping from one energy level to higher energy, another energy level, so there were few. We have seen that in the laser emissions also, from E2 to E3 or E3 to E2. When it is jumping, there are quite a different number of possibilities you have it, and each of these possibility having like a different colors also associated. So there was question like, some of these spectral lines which is jumping from one energy level to higher energy level, it with respect to intensity. So there was now no clarity in the Bohr's basically. Okay, so the more Bohr model treats electron as if it were miniature planet with definite radius and momentum. This is direct violation of the uncertainty principle, and we will see what is uncertainty principle little while. Okay, so which dictate the position and momentum cannot be simultaneously determined. The Bohr model gives us basic conceptual model of electrons, orbits, and energies. The precise details of spectra and charge distribution must be left out to quantum mechanical calculations. So this Schrodinger equation and all that you'll get it in next slides basically. Again, this quantum Compton scattering, this I'll leave it to you. So you know about this Compton scattering right from the 10th standard if I'm correct. Okay, so I leave this also. because we are not going to be discuss every of these values. The first important is more the black body radiation, that is important. You need to understand that one, and photoelectric effect. These two I'm compiling for you, and the other I will just leave it to you with this slides itself. You can actually go through it. Now, this is an important concept. This slide is really important. So wave particle duality, basically, does light consist of particle or wave? When one focus upon the different types of phenomena of light, if you look at, then you can actually, which property explains both particle nature and wave nature. For example, reflection. The reflection can be explained by wave nature, and it can be also explained by particle. Refraction can be explained by both, actually. Okay, wave nature and particle nature. But when it comes to interference, diffraction, and polarization, these three can be explained with only wave nature, but no particle nature. Particle nature cannot be explained with this. Okay. Now, when it comes to photoelectric effect and Compton effect, this can be explained with only particle nature, but not with the wave nature. So most commonly observed phenomena with light can be explained by waves, but the photoelectric effect and Compton effect suggest a particle nature of light. So these two are actually triggered and change the total dynamics, basically, because reflection and refraction explaining both. Okay, so and the photoelectric and Compton effect are telling you precisely light is also composed of light particles. That is what is very interesting here. Okay, so then electrons too were found to exhibit dual natures. So that is one. So this is another thing. Okay, so particles are waves. The de Broglie hypothesis proposed that essentially no separate in between, that all particles, not just only waves or not just only the electrons, all these can behave like same photons as well as wave. So it can behave like both. More precisely, if light waves of frequency mu can behave like a collection of particles, that is energy E is equals to h mu, then by symmetry, a massive particle of energy E, that is electron, okay, can also become like a wave. So the question basically, like, if light, the question was, in the many of the experiments was asked like whether light is a particle or wave. So initially people thought that it is a wave. So it is proved that it is a particle by photoelectric effect and Compton effect. Now the question this needs the de Broglie asked is, okay, light is a particle as well as wave. Fine, this is understandable and it has been proved. The next question is, what about electrons? What about electrons? Can electrons only a particle? That's the question he asked. So he asked the question that can electrons also behave like a wave? That is the question asked, and he said it is indeed a wave also, he said. So it is that's where he proposed a concept called matter waves. So he said that any particle in the nature can be treated as a matter wave. Okay, so for a particle, a light or a photon, right? So the wavelengths associated with this lambda is equals to c by v. Okay, so what is it for a massive particle? For example, you take this yeah, here you can actually get a very simple example. Let's say if you take a small ball, you can take it as kind of football, you can take it. Okay, so what is the mass of that one? Mass of that one, let's say 150 grams or 0.15 kgs. Okay, and imagine that you are kicking that football with the velocity of 40 meters per second. Okay, and you can convert that into whatever the units you feel like, and calculate the wavelength associated with that particle. Okay, but with that football, lambda is equals to that h by mv. M and v, and this h value. If you calculate that wavelength associated with that football, is basically comes somewhere like this 1.1 into 10 to the power of minus 34. Okay, so this is what is the wavelength, minus 34 meters, remember. Okay, now take the electron. So electron, and you put some, you accelerate this electron with some electric field, that is voltage 100 volts. Okay, and corresponding velocity you can get it basically. If you know the voltage, then you can find out what is your velocity as well. And same apply to the wavelength. Lambda is equal to h by mv. Okay, and if you find out the wavelength of that electron, it comes like 1.2 into 10 to the power minus 10, which is nothing but 0.12 nanometers. And compare these two. Compare these two. An electron having wavelength in the order of 10 to the power minus 10 meters, and same the particle that is a football having the wavelength 10 to the power minus 34. Okay, so what de Broglie said that each particle, whether it is a microscopic particle or macroscopic particle, definitely associated with the wavelength. But when it comes to macroscopic particles, let's say football in this case, the wavelength associated with that football is 10 to the power of minus 34 meters, which is very, very, very small. You cannot actually experience that wavelength. That is the problem. Okay, so although there is a wavelength of, that's a wave nature is associated with that particle, but you cannot feel that wave nature because of the extremely smaller wavelengths. Are you getting? But when it comes to electron, this wavelength you can actually, by some sort of experiment, you can feel what is that wavelength of that. Are you getting? Is this idea of comparing with the football and the electron and compare and calculating the wavelengths, have you understand why it is you will not be able to feel? For example, I and you also can have the wavelength, but the wavelength, you just take your weight and velocity with which you move, and then you calculate your wavelength. Now, so to get interference and diffraction, what is the wavelength you're supposed to take? What is the aperture you're supposed to take? This is the order. Can you get that order? Are you getting? In order
Yes, sir.
in order to experience the wave nature properties, which is interference, refraction, and polarization, you need to use this extremely small slits. So therefore, you will not be able to see wave properties with you and I, and with any macroscopic particles. That is the problem you have it, because the wavelength is very, very small. Okay. So de Broglie said that the wavelength for a macroscopic particles are negligibly small. This extreme or effective important this wavelength is actually you can experience when it comes to microscopic particles. Therefore, you can feel a wave nature in the microscopic particles, such as protons and electrons and neutrons, all these. Okay, or alpha particle, all this. Okay, is it clear what is that de Broglie said?
Yes, sir.
So
Yes, sir.
yes, please. Yes, somebody has some doubt? All right. Okay. Now, wave particle are such objects that are large in the absolute sense have the property that the wavelength associated with them are completely negligible compared to the size. So, therefore, large particles only manifest their particle nature. They never manifest their wave nature. That is the kind. Okay, and matter wave. The previous set of examples shows that number of experiments were done at the beginning of the 20th century whose results cannot be explained with the classical mechanics. Each of these experiments were prescribed or described a set of postulates, and again, none of them postulates cannot be justified by the classical mechanics. So the final conclusion what you have is each of this matter wave, any particle, is associated with the quantum the quantization principle of the energy, that is E is equals to h mu, right? So that is what is important. Another thing, the each of these particles are associated with the wavelength, that is what is known as matter waves. So, and these matter waves only can be experienced, or a particle can behave like a particle at certain wavelength, but it can also behave like a wave nature at a certain different wavelength also. Okay, so this is what is de Broglie hypothesis. So de Broglie momentum, that is B is equals to H cross K. So this is what is actually de Broglie momentum, we call it as. So this is one of the important thing. Okay, so and for this matter wave there are experimental evidences we can have it. So that is basically this particular experiment I have talked to you about, double slit experiment. right? So when you deal with the electrons, you can also feel the interference pattern on that. I think in the very early classes I have spoke about this in the in our introduction classes. I hope you remember that. Okay. And there are certain experimental evidence also you have it, the electrons also can have the diffraction, and the neutrons also have the diffraction, all these. Okay, so this is again another thing, we can skip it here, but only the fact that there are two more confirmations you can have it, that are the Thomson experiment and Davison-Garner experiment. These two I will talk about in the next class to tell you about the dual nature of the electrons. So these two has confirmed by the Thomson experiment and Davison-Garner experiment. These two experiments we'll talk about, and then we'll move on to Schrodinger wave equation and uncertainty principle, all that. Okay. So with this we will wind up today's class, and if you have any doubt you can ask me. Yeah, you can stop your recording, Jindal.
Okay, sir.
Yeah. If you have any doubt you can ask me.